question shouldn't be too difficult to answer. But I can give you some context about, like I was saying, what our systems are. Hundreds, maybe 1,000 or so systems. They're all talking to each other, they're all reacting to signals, and those signals might end up in a trading decision, opening an order or something. So we care about the latency of that, because if you're too slow to do that, you might open an order that loses you money, versus making you money, and so it's a direct business kind of motivation to have low latency. So we're going to take a case study of kind of where we were with a bunch of our systems about a year and a half ago. And we were in a situation where a bunch of our systems did have some metrics, some sort of ad hoc metrics, but many didn't. And you know, we couldn't always see with great detail where we were slow, where we were fast. You know, worse, we suspected that we were slow and it was impacting the performance of our system. And this is kind of where I got on board with this project. I was asked to help out. Was when work had already started on some sort of new standard way to record these metrics. Okay, so pretty standard stuff. So I'm going to introduce you to this kind of this approach. It says first approach. I mean, we had other approaches. But this is our initial approach to do it in a standard way across all our services. So it's a kind of system that the application was responsible for gathering all the context, taking the latency and sending it to another channel, consumer, which would then bulk that up, send it over SNS, eventually into a database, which it was kind of built towards capturing every single latency trace. So anytime we had some sort of interesting latency happen in our system, we'd record this trace, it would find its way through these batches into this database. And later on, we also added kind of an ability to work with aggregate data. So yeah, this is kind of a little diagram of what it kind of looked like. So the outer box there is a single service, a single Rust service. It's responsible for sending this latency over a channel to another Tokyo runtime, which was the library we used, KLP metrics. And then that would be batching up all these things it received into big payloads, sending them over SNS, publishing it to SNS. And then Lambdas would consume that. They end up inserting that into a database, a ClickHouse database, which was TinyBird. And then Grafana can look at them all. I think it can do queries over that latency. You can end up with, you know, a dashboard showing you, okay, in the last day I've had this kind of P99 or whatever, right? So pretty standard stuff. And it worked. But it had problems. And this is what I think is kind of interesting. So one of the first problems we had before we even moved it into production was we found that adding this recording of latency, adding just these blocks that would send this latency over, would actually significantly impacting our performance under load. So when we stressed our system with load tests, we found that throughput was significantly impacted, latency was significantly impacted. And this is kind of insidious, because if you think about it, why are we putting latency measurements in at all? It's because we didn't know how fast our system was. So how do we actually know that we've made it slower by putting them in? You see what I mean? Because it's the measurement itself that's made it slower, and yet it's the measurement that tells us how fast it is. So this might kind of keep you up at night.
Does not agree.
If you just add latency metrics, you might be slowing down your system and you'll never know. The reason we knew is because we also wrote black box benchmarks of the system to load test it. So they weren't dependent on the latency metrics. They could also measure the runtime. We saw that with metrics in, it's way slower than without. So, okay, we're still trying to get this over the line. So mitigation was the throttle there. We put like a water. We put like a atomic integer into this critical path. I'm talking about the hot path. I'm talking about our service. The service is doing a critical function, right? And during that function, it has to send over some latency metrics, right? right? That's the critical path. That's the bit that we really care about. And that was the bit that was getting slower. So we throttle it, so when it under load, we only send a certain amount of metrics. Metrics are kind of nice in that we don't mind if we drop some of them, right? We certainly much rather than slow down our system, is to lose a little bit of metrics, end up sampling it. So we throttled this, and that gave us acceptable performances. But our problems didn't end there. The next problem we saw was, again, under load, out of memory. So once you load it up, tons of events are happening, tons of latency metrics, traces are being recorded. And they're getting batched up by, okay, we solved the hit on the hot path, and the critical path, if you like. But then, even when it's in the KLP metrics runtime, we're still producing too much data. We're batching up all this stuff, trying to send it to our message queue, which in this case was SNS, which actually was not appropriate for this task, but it is what we used at the time. So what happens if it can't keep up? Well, at the time it was designed to avoid data loss, so it just spawned more tasks, more published tasks, which would retry, and SNS would get slower and slower and slower. All this would build up in the heap. Eventually it would hit some container limit, and the whole service would go down. This is really bad. I mean, obviously it's really bad, but it's even worse if you think it's metrics that are bringing down some sort of critical service. It's not even the actual thing the service is meant to be doing. It's just us trying to track it. So short-term mitigation to this, if you compress the batches with something like Z standard, then you can get a higher throughput. That's cool. Doesn't solve the problem though, and then dropping data. So once we've got too many tasks backed up on the heap, we just start throwing them away. And again, that's a better solution than crashing or using up tons of memory, because it's metrics and we can afford to lose it. Next problem. Okay, our services are working okay. We're publishing stuff to SNS. They're getting consumed, they're getting into our database, and we can see them in our dashboards. But, so now we're ready to push to production. We push to production, we've got lots and lots and lots of services, right? So, and lots and lots of real life load. And it's all building up in our database, and we're finding that us queries are getting too slow, because we're just building up so many traces of latency in this database that querying over them is just not working out for us anymore. So to mitigate, we get our runtime to publish aggregate data instead of all these traces, and we use that, and that helps a bit because aggregate data is a lot lower and it doesn't scale in the same way. But our problems aren't quite over yet. Finally, it was the lambdas. So we have lambdas set up to consume from SNS. Again, another load issue. This is kind of interesting because the lambdas could keep up with the load in terms of performance, but they just cost absolutely shitloads. And it was like something like estimated as like 20K a day. Again, it's all like metrics. So
that's cheap for metrics, isn't it?
So yeah, our short-term mitigation was to just delete all the lambdas. Death for the whole thing, and it all stopped working. There was also a couple of other things we weren't happy with the code. It ended up being quite intrusive. Again, metrics. The service is already doing something quite critical. The code should be mostly focused on doing that critical thing. Metrics should be a fairly light touch. So not only performant, we wanted to be a kind of light touch on the code. Also, our old solution required a bunch of configuration, which I won't go into. This highlights kind of an interesting thing about when you're designing a whole pipeline of data and how it can scale. You really need to consider every single part of the chain. Even if we design the initial chain better and it could handle tons and tons of load, if our message queue couldn't handle it, then it's a big problem. And we have to think about that. If we upgrade our message queue, so now it's like really, really good, it can handle tons of load, maybe our consumers cost too much, even if they can handle the load. Maybe our message queue is going to cost too much. Is it worth it for what we're even doing? And we decided it wasn't in this case. So we decided to come up with a new approach. It's actually quite a difficult thing to do in a company because you have to admit that your approach was wrong and you've been talking about this whole time. But when it goes bad enough that you have to turn it off, and you get the opportunity to rethink the whole thing, the lessons you learn. And yeah, the second approach went a bit better. But here were the objectives. So learning from what went wrong, I wanted to minimize the overhead on the hot code. So the critical path, where we dispatch these latencies, it's got to be minimally affected by recording latency, because whatever it's doing is more important than recording latency. it's got we essentially want it to be unaffected, but minimal overhead. One of the things I wanted to look at was like, can I make the hotcode have zero allocations required when sending traces over? So I want the hotcode to require no allocation at all. Allocations can happen a little bit later on off that critical path, but that was one objective I wanted to look at. And obviously I was successful, otherwise I wouldn't mention it anyway. No one was to bound memory use. We're talking about out of memory. There's lots of opportunities when you're handling high load to run out of memory. And we tend to, by default, try and minimize data loss. On a bound, but not only that, if you think about a system that's using a couple of 100 megabytes, you don't want 100 megabytes of that to be your metrics component. It's a less important thing. It's really, you want it to be very tightly bound in memory and to be very reliable, used across a wide range of services, which might themselves require a ton of heat, right? So, very good high quality bounds on memory usage, that's an objective. And then of course, yeah, scale, like I talked about with the other one, it needs to scale, considering the whole pipeline, all the way to whatever dashboards we need to be able to handle very high load today and 100 times more later. And of course we want to make it easy to integrate. So let's have a look at some of the code. I'm going to show you what it looks like to integrate this new service. You define trace points in an enum. So in this case, we've got a service which receives an event from an exchange, something like a trade event, something like that, from a crypto exchange or from a financial kind of market, and then outputs some indicator based on that event to 0 or like hundreds of gRPC clients. And what we're interested in this service is how quickly can it take that event, do whatever processing it needs, and then output it out the other side, right? So these are our 2 points, and of course it can get more complicated, but this is a good example. So we've got an enum, which is they're named and documented. They implement display, so that's involved when we publish them. That's pretty much it. And then to use the service, the service is going to initialize the able trace task, the channel, and it's going to define which points it wants to measure latency between them. A kind of interesting point of this, I wanted to minimize the impact on the code. So one of the things to support is you don't actually send latency measurements yourself, the application, it just sends trace points. So when the start event comes in, it just sends the start event has come in with this new unique ID at this nanosecond timestamp. And then later on, just before we output to some gRPC client, we, this is in another part of the code totally, we'll send the end trace. So we call it end because it's just the end of it. Call it ending. It's got the same ID we have to carry through our application, and it's got the nanosecond timestamp, right? And that's it. This is the entire code of the critical path. So why is it fast? What makes it fast when the previous one was slow? The previous version, which I haven't actually shown you, but I can describe it, it was a bit more generic, it was a bit more geared towards handling any amount of tags, any sort of things. And basically it had a bunch of allocation built into it. Had a bunch of string usage, box usage baked into it before it was even sent over to the channel. So just to construct that trace, this version of this trace, you had to allocate some stuff. And if we're trying to measure a process that itself is really, really fast, then having to allocate a bunch of things just to measure it can be slower than the task itself, and hence impact. This involves no allocation. New ID is a process unique ID. It's about 64-bit size, and it involves an atomic increment. Obviously, the trace name start is just an enum, and then getting the received nanosecond timestamp involves just a system time, right? And so also not quite as fast as an atomic, but pretty fast. The struct itself is then quite small, like 24 bytes, and sending a small struct over something like a Tokyo MPSC channel is very fast. Okay, so the whole thing ends up being very fast, order of magnitude faster than the surrounding code, and so it doesn't end up impacting. And that's a critical part of it. And then we've got the receiver task. So we're sending, all you send is like the start happened now, the end happen now with ID, right? So what the receiver task does is it receives these traces over the channel. It increments a rate counter, so rates, this many start events happening per second, this many end events happening per second. That's what it needs to. Then, if we go back to the one before, you can see at the top there, this is how we initialize the channel. When we're tracking latency between start and end, that means we're registering start as a kind of start latency point and end as an end. So when we receive a start point, we're going to record the ID and time of that start in a cache. And when we receive an end, we can look up by ID the start, and then we can add that end. We can compute the latency, we can add that to a histogram. Okay. And then every, so often every interval configurable, let's say 20 seconds, we take those rates, we take those histogram aggregates, and we publish them. So how do we keep memory bounded when we're doing these operations? It's relatively straightforward because the channel going into it is a bounded channel. You don't tend to ever hit that bound because you make sure the receiver runs fast enough. We store the start times in a linked hash map that we then drop the least recently used values. And then the latency is stored in histograms, which are pretty much constant usage because everything just goes into buckets. So it's fast on the hot path, it's fast enough on this path, and it doesn't use much memory. It uses a tight bound on memory. So let's go back to the bigger picture and see how it's done better than the previous one. So critical path is now fast, no throughput required, zero allocation. The receiver has fully bounded memory usage. We found it something like 12 megabytes. In most of our services, it depends on if we've got a whole bunch of other stuff going on, we might increase that. But now the interesting thing was, in our previous attempt to do it, we were trying to record all these traces in a database. But then when we found that the queries didn't work, we just used aggregates. And what we actually found out is that all we really need in a dashboard is aggregate data. We're really just interested in seeing like the average latency over some period, the P99 latency, and to track that over time. We don't need to store every single individual event trace in a database at all. And so this doesn't do that. Instead, like I said, it was going into histograms. Every 20 seconds, we just publish. So the time between start and end, the average latency is this, the P99 is this, whatever you want. Median is this. This is cool because, all right, I've changed the technology a bit. Now it's publishing over OpenTelemetry protocol into an OpenTelemetry collector, and then into data. But the most important thing is what we're publishing now has a constant size. So it's a report sent every minute, and it just includes the rates of all our trace points, and then the latencies we've asked it to measure. And if there's like 1 message a second going through the service, the report is the same size as if there's 1 million messages going through. And if you can do that, you're in a great position, right? Because all we need to do then is validate at any load that this part here to the right of the service is working. And we know that even under extreme load in production, that the rest of that will work well. Once we've solved the scaling problem in our service, we know the rest is fine. And it was good enough for our use case. So yeah, constant size load, it makes scaling a lot easier. We've also got rid of the lambdas and SNS, which weren't appropriate, and the database, and we were already using Datadog, so it just made things easier. Yeah, here's some benchmark numbers I took about at the time. You can see under a load test with the old system was hugely impacted by trying to measure metrics. This will give you an idea of really how bad the impact was. And kind of good that it's really bad in a way because it forces you to do something about it instead of kind of getting hand-waved away. And then we've got the second solution. We don't need to throttle it. It doesn't drop any data in the channel. And these benchmarks are, by the way, not including any publishing at all. This is just an in-process effect on throughput. With our new method, we found it doesn't affect anything at all. And yeah, this is kind of the output. This is kind of what we're looking for. It's presumably what anyone's looking for when they're running a service and they care about the latency. You want to see what it looks like over time. So this gives you an idea of what it looks like. I've highlighted a medium latency and a P99 latency. And we have this sort of historic data now for all our services for lots of time of operations. So yeah, what I thought was the interesting takeaway of this is that think back to how you design a pipeline. And you really have to, if it's going to handle any load at all, you have to really consider every single part of the pipeline. is it all going to handle load? And even if it can handle the load in a kind of performant way, is it going to handle the load in a way that you can afford? Like the lambdas, they scaled, but they weren't cost effective. The next thing I think is kind of interesting about this is, like if we go back to this one, we had to actually deploy to production to find out we didn't need to record all these traces. Like, we actually do need to do that in some other areas of our business. Like we capture data and we want to save it without data loss. So we do need to solve this problem in other places. But for metrics, we needed that dashboard. We didn't need to store a ton of metrics in the database. So we were trying to solve a kind of more general problem that we didn't really even need to solve. And we only understood that after failing to do it properly. But after we did understand it, we could figure out that actually if we understood the requirements better, we could do a simpler solution. It's way more cost effective. That's what we're doing. Yeah, we just need to see like P99 latency, average latency, median latency, stuff like that. Aggregate latency in the dashboard. And that's what we can achieve with this one. And the final point is, Rust is a great language to have you find yourself in this situation because you can do things like redesign something and say, okay, I don't want it to allocate. I don't want this piece of code to allocate at all. And you have quite fine-grained control of doing that. And it's something that you can achieve, whereas in like high-level GC languages, that can be much more difficult, or at least a little bit more horrible to achieve. So Rust is not always like super fast just by default. You might write it the first time, it's not that fast, but it gives you the tools to make it fast when you care about that enough. Yeah, that's it. Thanks for listening. Do you guys have any questions?
Yeah. You said you had to deploy it to production.